right, let's see here. I think I am live. We're gonna go with that I'm live. All right, hello everybody. I hope you're having a great day. So today I'm going to teach you all about how to measure the speed of light using a microwave and a chocolate bar because Halloween is tomorrow, so we're gonna try to get in the spirit. A little bit of bonus points to whoever can guess what my pumpkin is. It is based off a Disney character, but it's a little rough, so any bonus points, who can guess that? Okay, so first off, let's learn a little bit about wavelengths and the electromagnetic wave spectrum. So I'm going to get out my handy whiteboard here. Also, my camera lags a little bit, so hopefully it doesn't too badly. Okay, so there is this thing called the electromagnetic wave spectrum, or the EM spectrum for short. EM spectrum, okay? And there's different wavelengths. So it kind of goes like this. We go longer wavelengths, it gets a little bit shorter, and then we're gonna dot it, and it keeps getting closer together and closer together and closer together. Closer together, they stay, okay, we're gonna try this one more time. They stay the same height, but they start getting closer together. So let's try this more precisely. They're going to get closer together like this, okay? And then they get super close, okay? These are all the same height though. We're gonna pretend that that's the same height. Alrighty, so this is a nice spectrum and these have different names. So over here we have something called a radio wave. And then we go further in and there's the infrared or IR. And then down in between these two is the microwave, which is where we are going to be focusing at. So it's right here in between the radio and the infrared. And past the infrared is that visible. And so this visible is what we see in everyday life. So it has those red colors, the rainbow, right? So the red, orange, yellow, green, blue, and violet colors. And that's actually a super small part of the spectrum. And then past the visible, you have ultraviolet or UV rays, which you've heard of whenever you put sunblock on, you're trying to block some of those out. And then X-rays, which you've heard about in imaging, and then gamma rays. Okay, just want to make sure those weren't all backwards when you're looking in the camera. So this is a little bit of a rough drawing, but you can see as we go, these have something called a longer wavelength over here, and then to a shorter wavelength over here. So let's go into that next part, what a wavelength is all about. So I'm going to go ahead and erase these. We can talk about the spectrum a little bit later, but as we're going to focus on, once again, is that microwave. Okay. Okay, so wavelengths. We are, let's see, going to draw just one little portion of what that whole spectrum was, that really rough spectrum that I was drawing. We're just gonna do a nice little loop-de-loop. Okay, so we're gonna take right here from this peak, and we're gonna go all the way back to the peak, okay? And that is going to be something called a wavelength. And it's going to be important to note for this that from the top of the peak down here to the bottom of the peak is a half wavelength because it is half of the full wavelength. Okay, so that is the basis. And so when we were looking at that spectrum, if you remember, the microwaves kind of looked like this. It was a lot further apart versus those gamma rays were super close together. Okay, so the microwaves have a lot longer wavelength than the gamma rays because the gamma rays were super close together. So those microwaves are a lot longer. And why this is important is because we're going to be able to actually measure those microwaves. We're going to be able to measure this distance right here. So how does a microwave work? We've all used a microwave before. Sometimes it's just to tell the time. My household does not use it to tell the time. Something we maybe will work on in the near future here. But a microwave actually emits those microwaves, and it actually passes in between here. There's this metal plate here, and so it emits it, and the wavelength goes in here, and there are special points on the wavelength. We're just going to actually kind of put it in here, and it's going to look something like this, not quite to scale. And there are certain points called nodes. Okay, kind of in the middle. At those nodes, your food's going to be a little bit colder. Versus at these top points, your food is going to be a little bit warmer. And why that is because at these top points, your food is going, the wavelength is actually moving. So I'm going to take this, if you can see, and we're going to pretend that, let me see, make sure you can see this, that this is that half wavelength. Okay, this is the half wavelength. The wavelengths are actually oscillating. So you can imagine it's kind of like a jump rope, and it's going up and then back down and up and back down. And so these nodes aren't really getting much movement. So that food's not being excited at those points. Versus at the tops and bottoms, there is a lot more movement and excitation at those points in the food. This can also be used in our experiment because we're going to be able to put food at those locations and see where it's going to be melted a little bit more. Sorry, attached to some cords over here. So let's see here. We are going to now get our chocolate bars out. Let me see, make sure there's no comments or questions. Okay, I think we're good. Okay, so, yes. Okay, now we're gonna get our chocolate bars out. So, just got a normal Hershey's bar. And if you're following along, just need a bar. You can also use a lot of different things. Some people use a bunch of marshmallows and you can line them up on the plate. You can use crackers, burn some crackers, really whatever you have that you want to burn little holes in. Burn's a little bit of a strong word, but just want to make some holes in. And you need a ruler because you're going to measure the difference between those little points that are being heated. Okay, so let's go and take this out. If you're trying this later, make sure to get a candy you like. Or if you try this after Halloween, you can try it on a candy you don't like. Okay, and this is an important thing you have to do in this experiment. You actually have to take the rotating plate out and to be able to see this. This is because whenever it's rotating, that is to try to balance out where it's being heated at. So everything is being rotated. So when those wavelengths are going, your food is rotating underneath it. So it's actually, your food is getting hit at different points. So we're going to take this rotating plate out. Let's see. Okay, put the chocolate bar in. Okay, I'm going to go and put it for 30 seconds. And it's rotating. That's not what I want. flip this plate upside down. Okay, there we go. So I had to flip the plate upside down. There's still the little piece that's in the microwave that was turning it. So can't quite see if it's making the holes, so we're just going to trust the process here for 10 more seconds. I believe you can do it for a shorter time, but more is sometimes better, so we're going to see. All right, let's check this out. Yes, perfect. Definitely smells a little burnt. If you have a graham cracker and marshmallows, this would be even better. Okay, so you're going to take your ruler. We are going to use the metric side, so the millimeters and centimeters side. Let's see if you can see this. Yes, you can see that. You see those holes? That's kind of cool. Okay, so now we can see those hot spots. So these are actually going to be those half wavelength spots that we were talking about. So we're going to go ahead and take our ruler, and we're going to go ahead and put it on here. And I'm measuring for about the middle of each of these spots. So see if you can see these. So I would say it's about oops, that's something. There we go. Okay, about 6.5 centimeters for the middle of the two spots. So you may be asking, okay, great. I know the distance between those spots. What do I do now? Is that the speed of light, Alyssa? No, that is not the speed of light exactly. You need one more value. So the distance, the half wavelength, equals 6.5 centimeters, which means that the full wavelength equals 13 centimeters. Okay, next up, we are going to need the frequency. So let me back up. I'm going to write in red the equation for the speed of light. The equation for the speed of light equals, it is actually the frequency of that microwave times that wavelength. Okay, so now it's time to go over what the frequency is. All right, let's see, I think we just got a comment. Okay, so frequency. Frequency is in units of hertz. What the heck is a hertz? Let's see, I lost my little fake wavelength. Okay, we're back to our little fake wavelength. Hertz is in units of cycles per second. So we are going to take our little wavelength and describe what a cycle is. So a cycle is when you go from all the way, a cycle is when you go from here, here, and back. So on a wavelength, go back to it's going to be when you're going to oscillate all the way back through. So we're going to just do a little practice example, and we're going to see what the frequency is of this little example. So I'm going to get my little stopwatch out, and it's going to be a little delayed because of this, but I'm going to go ahead and start it and go 1, 2, stop. Okay, so that was 2.2 seconds. Okay, wrong color. This is just a little extra math for us. So we have one cycle for 2.2 seconds, which equals 1 divided by 2.2 equals 0.45 hertz. So that's just one value, so you kind of saw what 0.45 hertz looks like. Now we're going to see what the frequency of the microwave is. So we're going to go back here behind the microwave. Actually, I'm going to tell you where it is on the back of the microwave because this is a little hooked up. So, yeah, okay, so if you look on, no, we're gonna take you off. If you look on the back of the microwave, everyone see the blue, hopefully. I'm hoping you can see where it says 2,450 megahertz. Hopefully you guys can see that. Can someone comment if you did see it? Maybe. Okay, we're gonna go with yes. So the microwave that I used was 2,450 megahertz. So just so we know how big a megahertz is 1 million. So that means we multiply 2,450 times 1 million. Oh, it was too blurry. Okay, I'm sorry, guys. So for you guys doing it at home though, check it on the back. For me, it was like at the bottom part of it, and you're looking for something that says megahertz. Most microwaves are 2,450 megahertz. That's the pretty standard right now. But yeah, check that out. It's right next to where it says, mine says 900 watts. Okay, so let me get this back. Okay, so we now know our frequency equals 2,450 megahertz. So think about how fast that is. 2,450 times 1 million. When I did my little experiment of just doing this, that was 0.45 hertz. Can you just imagine how fast the 2,450 times 1 million is? I can't even fathom how fast that is. So we are now going to multiply these together. And so we're going to take this 2,450 megahertz for our frequency, and we are going to take our 13 centimeters for our wavelength. And when we plug that in, let's see, make this a little bit nicer. Let's see. Let me just make sure I got my units right. Okay. Go 2, 4. Okay, so we're gonna go, this was our very large number. So 2,450,000,000, this was hertz times 13 centimeters. And we are just gonna go ahead and plug that in right now to our calculator. So we're gonna go 2,450,000,000 times 13 centimeters is, it wrote a little large, but that is 3.185, let's see, times 10 to the 10th centimeters per second. Yes, so let me make sure. Can you Google the model number? You guys got it. Okay, so it was 3.18 times 10 to the 10th centimeters per second. And so the model number for the speed of light is about 3 times 10 to the 10th centimeters per second, which is a pretty close number. And so, in other words, that is about 300 million meters per second. So the speed of light moves at about 300 million meters per second. I don't know about you, but I probably run at about 2 meters per second. Just kidding. I don't know how fast I run, but 300 million meters per second is fast, and the speed of light is the fastest thing around. And so, yes, congratulations. We have now calculated the speed of light using your microwave at home and your chocolate bars that hopefully you've gotten from Halloween, and you can now enjoy. I'm gonna check and make sure that there's no more questions. Let me go through. Oh, type of chocolate bar. Yes, Hershey's. And I had a backup Hershey's of Hershey's with Reese's. Yes, so I think I might do this one after. I did see someone has done it with 2 Hershey's bars next to each other so that you could do a few test points. So there's 3 test points and you can measure the distance between all of them. So that could also be something else you do. All right, I think that's about it. If nobody else has any other questions, thank you all for listening and I really appreciate it. Have a good rest of your day. Bye guys.